So, click OK. Okay, let's get started. I would like to welcome every one of you, the people who are present here with us, and also the people who are online. My name is Abdullah Kiwan. I'm a researcher at GTArc. My main research interests are natural language processing, generative AI, and then large language models. You are now here at ZEKI. It's the Center for Tangible AI and Digitalization. So I will speak briefly about ZEKI, what it is in general. So we are focusing on 3 AI domains: autonomous mobility, smart spaces, and cybersecurity. We have a lot of interesting projects, like one of them is BeIntelli, that's running currently. That's mainly interested in explanatory bus and delivery robot and also other components. So BeIntelli is mainly about autonomous cars. So we have those autonomous vehicles, and we are doing experiments with them, explainability, and also other kinds of applications. We also have an important aspect in ZEKI, which is the smart space real lab. Here, our workspace is equipped with a lot of AI applications like multi-sensors, conversational assistant, test booking systems, and many more. Here are some photos for ZEKI. So ZEKI is mainly an association with many members from industry like GTArc, Huawei, Mercedes-Benz, Continental, and many more companies. So the meetup for today is in the context of a project called ZEKI. So the main purpose of ZEKI is to bring AI into the society, to make it closer to them. We have 4 pillars for the project. We have the real lab. As I mentioned, we have many applications there. We have the tangible AI and explainability to explain the AI algorithms. And we have also a software stack that we are developing at the moment. And we also have our platform and ecosystems. That's mainly about ZEKI project. And now let me get started with our paper for today. So it's with the title, Rethinking the Bounds of LLM Reasoning, Are Multi-Agent Discussions the Key? Today I'm going to give an introduction at the background, then a motivation, then related work, then the main approach, which is called Conquer and Merge discussion, benchmarks, then I will present the experiments, then a summary, and at the end a discussion. Let me first get started with an introduction and a background about the main terms that we might need for this paper to understand. So the main introduction is about large language models. So I will talk about what are LLMs, large language models, pre-training and fine-tuning, prompt engineering, reasoning in large language models, and then multi-agent LLMs. So we start by LLMs. What are LLMs? LLMs are basically artificial intelligence software that were trained on huge sets of data in order to be able to understand and recognize the human language and also many other complex types of data. Large language models were mainly trained on using a type of neural network that is called transformers in order to understand the combination and the relationships between characters, words, and long sentences. Large language models could be trained to do a lot of tasks, and one of the most common tasks for them is their application as generative AI. So what is generative AI? Generative AI is mainly when we give the model a question, we give it instructions, and the answer or the reply that we get it as a generated text. As we know, ChatGPT is able to write poems, to write essays, or even answer questions when we give them like a context of something. Now, large language models require 1 or 2 steps in order to work well. And those steps are pre-training and fine-tuning. Let's get started with the pre-training. Pre-training is the foundational process for large language models in order to obtain knowledge or understanding about the language. So through this phase, large language models would learn grammar rules, would learn factual information, or even reasoning abilities. Pre-training work in an unsupervised manner. So what does unsupervised mean? Sorry, unsupervised means that when we feed training data into the large language model, we don't give it like whether the data is right or wrong. We don't give it like annotation. It's just we give it plain text and it will learn from this plain text. One of the techniques for the unsupervised learning is called masked language modeling. This technique is mainly when we present a sentence to the large language model, we give it the sentence with some missing words intentionally, and then we expect or we ask the large language model to predict those missing words. And in that way, it will learn the language and the grammar rules. Fine-tuning is a step that comes after pre-training. So it's basically to make the large language model specialized in one domain for some specific task. So we give it or we train it on a specific domain data. So it's like transforming large language models from a language learner into a domain-specific expert. Now we move to another term that's prompt engineering. So what's prompt engineering? It's basically formulating the instruction or the question that we give to the large language model in the best possible way in order to get the most helpful answer. So all the instructions or the questions that we give to the large language model, we call them prompt. And the prompt engineering is basically the process of designing this prompt in a good way. Let me give you an example. If you ask ChatGPT, what is a PMS? If you notice the answer at the beginning, that PMS can refer to different terms depending on the context. So ChatGPT could give me like many answers, but the accurate answer would depend on the context. But if I improve my prompt, my question, and ask it in another way, what is a PMS in the travel industry? Then we notice that we get more accurate answer from ChatGPT. In this example, we improved the prompt, and that's prompt engineering, basically. Now we come to a term that's called reasoning. So what is reasoning? Reasoning is basically a logical process to draw conclusions and make decisions based on some existing knowledge. So we will have those two examples. One person could be at one place at a time. This is like a type of reasoning that's called common sense. It's basically to simulate the human understanding of the events like in our daily life. Another example is if I put my hand in a fire, then it will burn. So reasoning is basically like to have those conclusions, I would say. Are we able to apply reasoning in large language models? So here is like an example about one of the techniques that's called chain of thought prompting. Chain of thought prompting is basically a powerful technique that has proven promising results in improving the reasoning abilities of large language models. So this type of approach basically involves generating multiple intermediate reasoning steps for the large language model. Those steps would guide the large language model to generate the good answer and arrive at a reasoning correct answer. So if you take here this example, this is like a standard prompt. I ask it a question, okay, then I give it like an example. I'm able to give the large language model an example to follow, and here in this example, I'm just giving it the direct answer. So the large language model cannot draw like good conclusions, but if I use the chain of thought prompting, I tell it here like in order to find the answer. So Roger started with 5 balls, 2 cans of 3 tennis balls, each is 6 tennis balls and 5 plus 6 equals 11, so the answer is 11. I gave the large language models those steps. So this is chain of thought prompting. So there is a way to improve the abilities in reasoning for large language models. My last introductory term is called multi-agent LLM. So multi-agent LLMs basically refers to a combination of multiple agents, each empowered by large language model. They work collaboratively. So instead of me having one large language model that would do a task, then I will have multiple large language models, each with its expertise in order to tackle a complicated problem. This was like an overview for many terms that we might use in our presentation, and we need them to understand the main topic of the paper, which is rethinking the bounds of LLM reasoning are multi-agent discussions the key. Let me get started by a motivation. So according to the paper, large language models still fall short in reasoning because of many reasons like hallucination and also some reasoning perspective mistakes. And the recent progress in the research suggested that using multi-agent discussions could improve the reasoning abilities of large language models. What is basically multi-agent discussion? So multi-agent discussion refers to an interactive setup where we have multiple agents, each one is based on a large language model. They will engage in a conversation. And those agents will carry on their conversations in an independent way. So this image illustrates like the four main components of a multi-agent discussion. The first element is a kickstart prompt. So this prompt is basically the first prompt that we give to every agent. It contains a lot of details about some knowledge about the task that we want to solve. And then we give those prompts into the agents that would collaborate together and talk together. We have the algorithm, which is an important component in this pipeline, and the algorithm specifies some rules for the discussion, like the structure of the discussion, number of rounds, number of agents, and also it specifies the decision-making algorithm. And the last thing is the result. After coming to the final answer, then we need a way to render and present this answer. Now, before I start with our paper, I would like to present three related work papers. So the first one is the debate, the multi-agent debate framework, then MAD multi-agent debate, then reconcile framework. So the first one, the multi-agent debate framework. This framework basically involves multiple LLMs that will debate with each other. So how this thing works? It's basically, we start by having like a prompt, and we ask every agent to generate its candidate answer for the problem. That's for the first round. We ask every agent to generate an answer. Then in the second round, every agent would look at the answer of all other agents, and it will use those answers in order to update its own answer. So, and this process would be repeated for many rounds. Now the second framework, that's called MAD, multi-agent debate. So this framework solves the problem of degeneration of thought. So this problem is about, like, when the LLM establishes confidence in its answer, it's unable to generate novel thoughts later through self-reflection, even if the initial stance is incorrect. So this framework basically involves only two debaters, only two LLMs. One of them would be like affirmative, like here, like this character, and also the other one, the angel one, would be like a negative debater. What does that mean? That means this angel will try to disagree with the other debater, or else try to convince it to correct its answers. And we have a third role in this framework that's called the judge. And this judge would basically monitor and manage the discussion between those two agents in order to come to the final answer. That's basically the second framework. The third framework is called Reconcile framework. So this framework basically incorporates different families of large language models like ChatGPT, like BART, and it will also incorporate a confidence for every agent. You could see here, like every agent would generate an answer, for example, yes or no, with a confidence. And those confidences would be used for the weighted voting mechanism at the end to choose what is the final answer that we want to get. Okay, that was like the related work for our paper. Let me get started with our approach, with the main approach of the paper. Some motivation. Why do they work on this approach? We have two motivations here. So the framework that I already mentioned, they all claim that using multi-agent discussions would improve the reasoning abilities of large language models. And this paper actually wants to re-evaluate this claim through more analytical experiments. Another motivation is that number of frameworks for discussion is still limited, and none of them consider the very important type of discussion, which is called group discussion. So this framework also introduces this novel kind of discussion. So how this new approach works? So it consists of 3 stages. In the first stage, we have all the agents. Let's say we have 6 agents. We divide the agents into groups, and all the groups would have equal sizes. We ask every group to solve some problem using discussion. Every agent within a group is able to see the answers of all agents within the same group, to see the full explanation, the full answer that is generated. But every agent within a group will only be able to see only the answer from different groups, only the last answer, no explanation is provided. So this stage will last for multiple rounds. Then we move to the voting stage. And this voting stage, actually, the answers of all the agents would be treated equally. That means we take the answer with the majority of all those agents. And in case of equal number of generated answers, like 3 said yes, true, 3 said false, then we move to a final decision. In this stage, for the final decision, there is a new role that's called secretary. Secretary is basically a large language model. It will take the explanations and answers from all the agents with their answers and find the final answer. So for sure, we have to evaluate every approach. So we need benchmarks. So in this paper, they use 3 benchmarks. The first one is called ECQA. This benchmark contains common sense questions. Like here is an example of this benchmark. What is something that people do early in the day? So we have 4 options, 4 choices. So make tools, or eat eggs, or skydive, or smoke pot. So person could do a lot of stuff in the morning, but among those answers, so eat eggs is the correct one. The second benchmark that is used is called GSM 8K. So it's about math word problems. Here is an example from this benchmark. Tim grows 5 trees. Each year he collects 6 lemons from each tree. How many lemons does he get in a decade? So the answer is basically we multiply 5 by 6 equals 30. 30 lemons per year. Then 30 we multiply it by 10 for 10 years. In the decade, then we have 300 lemons in 10 years. So this benchmark contains similar problems. Third benchmark is called Foley Wiki. It's a deductive reasoning. So deductive reasoning is mainly we have many premises. We have a hypothesis, and we want to know whether this hypothesis is true or false or even unknown. We cannot come to this hypothesis given those premises. So this benchmark contains such examples. Now, let's move to the experiments. We have 3 experiments that this paper did. So in our first experiment, those experiments were done on single large language model and fully wiki data set. So here I mean by single LLM that we have definitely multiple large language models, but they're all of the same family of large language models. But here in this experiment, for example, they're all ChatGPT 3.5. So they started by only one benchmark just to gain the initial insights. And for the prompting, the authors used the strongest prompt that was applied on this data set. So this prompt contains detailed question description, an answer format description, and also a task-specific demonstration. In the world of large language model, demonstration means that we give the large language model within the prompt, we give it one examples or a few examples in order to, those examples will help the large language model to guide it to its final answer. So basically every demonstration is a pair of question and answer. So here's the table, the findings of the first experiment. For the prompt components, the authors experimented with different components. Sometimes they only use the question description in the prompt. Sometimes they use the answer description, sometimes both of them. And lastly, all of them would be present in the prompt. And they experimented with MAD framework that we already talked about, the debate as well, with the 3 agents, the debate with 6 agents, and lastly, CMD is the approach that we are talking about with 6 agents. And we also did the comparison with only one single agent. Our first finding is that CMD performs better than single agent setups and other multi-agent discussions. That happens when we give all the components of the prompt. You see here that CMD is having the highest accuracy among all other agents and frameworks. Our second finding is that a detailed question description or task-specific description enhances the reasoning abilities for both single agent settings and multi-agent discussions. We see here that, for example, this number is higher than all other numbers. Why? Because this number, here we use all the components of the prompt. So introducing more demonstrations would improve the reasoning abilities. And same for single agent, for an example. Our third finding is that a strong single agent could be comparable to discussion frameworks. Like for one single, if we provide it with good demonstrations, good answer description, good question description, then it could perform similarly to other discussion frameworks. In the second experiment, we are experimenting of the framework on all tasks. Here are the tasks that I presented already: ECQA, GSM, 8K, and fully wiki. And then here we take the average. For every task, we experimented with once without any demonstration in the prompt, and secondly, with giving a demonstration within the prompt. We want to do a comparison here to see the effect of the demonstration. And we compare a single agent, we compare with MAD with the 3 agents, debate with the 3 and 6 agents, and then lastly, CMD, the approach with 6 agents. We noticed that with demonstrations, discussion frameworks and single agent settings have comparable performance on average. We could look at it here. So with demonstration here, 75, and here, 74. there's not big difference. So sometimes that single agent would be able to perform very well with demonstrations. Now, without demonstrations, CMD would surpass the single agent settings. You could look at it here. So here, direct. So it's without demonstrations. For the CMD, it's 70, and for the single agent, it's 67 accuracy. So there is a big difference. So why does discussion work better without demonstration? So when we don't have a demonstration, every agent would get input from from the explanations of other agents from previous rounds. So this could introduce a new perspective to the agent through the reasoning process. And for that, we have like a nice conclusion here, which is multi-agent discussions are more effective option in scenarios where we don't have specific expert knowledge or detailed examples. In some cases, in real world, sometimes we don't have enough examples to give to the large language models in order to learn from. So in those scenarios, using multi-agent discussions would be a better option. We have also like another here use case that I would like to discuss, which is through the experimenting, multi-agent discussions could give wrong answers for questions where single agents would be able to give the correct answers. So what is the reason behind that? So there are, in the multi-agent discussions, we noticed that there are two types of errors. So judge mistake and wrong answer propagation. So if you look at this image, so we have a question and the correct answer is unknown. So here a single agent could give a correct answer, which is unknown. If we have a discussion here, there is agent 1 that gave unknown and agent 2 gave false. So the correct answer is unknown. So the agent 1 answered correctly, but when we reach that judgment step, then the judge gave false to this question. So that's the judge mistake. So this error came from judge side. That's the first type of errors. Another type of error that's called wrong answer propagation. So agent 1 gave unknown in round 1. Agent 2 in round 1 gave false. However, agent 1 in round 2, in the second round, changed its answer to false. So here a wrong answer propagated through the round. So that's also another source of errors that could happen in the multi-agent discussion frameworks. The last experiment is using multiple LLMs. So we don't only have one type of large language models in the group discussion, but rather for every group we have 3 types or 3 families of large language models: ChatGPT 3.5, Gemini Pro, and Wang. So again, we experimented on all tasks. For every task, we experimented with a direct prompt without demonstration and also a prompt with demonstrations. We considered the average for all tasks. We experimented with single agent, bar, Gemini, ChatGPT, and the group discussion framework, the CMD one. And also we compared it with Reconcile framework, the third related work framework. Our first finding in this experiment is that a strong single agent is comparable to discussion frameworks. We could look at it, for example, here. Gemini Pro is the strongest LLM. It has an average of 78 with demonstration, and it's also comparable to the group discussion, 78.66. When we don't have demonstration, then discussion frameworks would outperform single agents. So this is something we could look at here. Okay, when in the case of direct, it's 76, but the best LLM gave 74. So there is a difference when we don't bring demonstration in the prompt. Now, the third finding in this experiment is that stronger LLMs would enhance the performance of weaker LLMs through the discussion. Here in this graph, we track the performance of every large language model, of every single one, in every round. So BART, for example, started with a weak performance in the first round, then it improved in the second round, then it's roughly approaching the performance of other stronger large language models in the third round. And that was for reconciled framework, and the other example was for the CMD group discussion framework. So it's basically when we have multiple LLMs discussing with each other, we have one very powerful and one which is weak, then performance of the weak one will get improved because of involving the powerful large language models in the discussion. Now, as a summary for what we have talked about. So the main result is that single agent, single LLM, with a strong prompt and powered by a strong LLM would achieve comparable performance to multi-agent discussions. When we don't have demonstrations, when we don't have enough expertise knowledge in the domain, then multi-agent discussions would outperform single agents on most tasks. And third one, when multiple LLMs are involved in a discussion, then weaker LLMs would get improved by the more powerful large language models. So the paper also addressed some future works. First one is to enhance agent complexity. Nowadays, there are large language models that are able to call and use external services or external tools. Like, for example, there's one called Gorilla that's able to call functions from Hugging Face. So integrating those large language models could enhance the multi-agent discussion. Another future work would be to expand the tasks. Now we experimented with reasoning tasks, but there are more complicated tasks like strategic planning, where having a multi-agent discussions would be a good option here. And also experimenting with additional large language models. As a last message, every approach would have its challenges, for sure. And for this type of approach, one of the challenges is that it cannot be applied to real-time applications. In real-time applications, we need instant answers. We cannot wait for the group of LLMs to finish discussion. And also, it's computationally expensive. So we are using multiple instances of large language models. That's expensive. But on the other hand, it has also some advantages. It reduces the likelihood of false conclusions and hallucinations. So, for example, there are applications where we need very accurate content, for example, in the applications of fake news detections. Then here, the input from multiple LLMs would correct the information that are retrieved for the news, for an example. Another advantage is that adaptability. So this kind of framework is easy to adapt to any large language models because we could consider large language model as a block box that takes input and generates output. Also, diverse perspectives. We could experiment with large language models in some tasks where every large language has some expertise in some domain. For example, one large language model is very good in mathematics, another one is very good with languages, for example, and translation. They could collaborate together. So here what I mean by diverse perspectives. And also the collaborative learning. If we have weak large language models, we could involve them with powerful large language models in order to improve their abilities. That was from my side. Now it's time for discussion. Thank you so much. Any questions?
Yeah. There was in the slide when you mentioned about how stronger LLMs improve the performance of weaker LLMs. I think if you go to the graph, it looks like the weaker LLMs also are bringing down the stronger ones. So this, in both cases, it looks like ChatGPT performed, or sorry, the Gemini Pro performed worse in the second round because
which one? Which framework?
in both.
Both.
Like look at the Gemini Pro went down in round 2 and then went up. So
but then it
discussed that also the weaker models are also bringing down the.
But then it went up again. Right?
Yes, but there is an effect of
yes, you're right.
So
you're right.
Was it discussed somewhere in the paper? Or?
No, they only mentioned the good good parts and good results. No, it was not mentioned at all. Yeah, question.
In German, we have a speech which is saying, in a group, the weakest part is defining the effectiveness of an output. So in general, I was surprised about the statement that the weakest part is just profiting from the others, because in effect we can see there's some high performance on the weakest part, but the best part is also giving us some performance.
Yeah, that's correct. That point should be addressed by the paper somehow. Right. Yep.
There was a second point I was surprised about, which is saying that demonstrations are in general not supporting by correcting the result. And did you make a research about the quality of the demonstration? Because I do not agree 100% about demonstration are not helpful and discussing is more useful.
That was mentioned. Okay, so here demonstration in general is something good to provide in the prompt of the large language model. Definitely the quality plays a role. In some cases, if the demonstration is not correct or it's not explaining well, then it doesn't bring anything. Maybe it could bring even more hallucination to the large language model. But here, like the comparison was like that discussion frameworks outperform single agents when there is no demonstration. Because okay, the single agent could benefit from demonstration. That's why it could perform comparably to discussion frameworks. But when there is no discussion, no demonstration, then the discussion frameworks would have something to rely on, like extra information, which is the answers and the explanations from all other agents.
But this is also another thing is that I understand that I think the demonstration would improve the results definitely for all of the types of the models or the discussion or without discussion or single agents. But the problem is with this discussion framework, in the absence of a demonstration, we're claiming that it's helpful and it's improving the results. But what if let's say that the demonstrations that were concluded by these models were wrong? They were making the results worse. I think that the problems that you mentioned, the end with the judge mistake or the propagation of the result, the wrong answers, could be a result of this. That the demonstration that was concluded somehow was wrong, and that affected the models, and that brings everything down. So I'm not sure if that's the effect again.
I'm not quite sure as well. But here you said something like demonstration was concluded. So actually, demonstration is not an output.
Not concluded, yeah, but I mean, it's like let's say that the demonstration alternative. Whatever helped.
Okay, you mean the answers from other agents?
Yes.
Yes, they could be. Yeah, they could have an effect. Like some agent was giving.
So I don't know. It would be interesting if there's a test performed where you compare them with both like a good demonstration versus bad demonstration, and then without demonstration, to see actually like if this has an effect or not. Like
I see your point. I see your point. That could be interesting. But I assume that all the demonstrations here in those data sets are correct or are of high quality.
We need test with bad quality.
Let's say, from my experience with large language models, I think wrong or low quality demonstrations would bring bad effects. But again, that's not like systematic experiments, but rather like personal experience with large language models.
I have a question to the first table you showed with the impact of the 3 different components for the description. Now the previous one where there was like, yeah, this one. There's the question description. Is this like addition? So they have, anyway they get their question, their product.
Sure.
So the question description is only some additional information about the question.
More detail, yes.
Maybe I missed it. Okay, need more detail. Okay.
Yes. Answer description is like in which format we need the answer to be. Detailed question description. And answer.
Yeah, but any details about how this detail looks like? Is it like a longer version of the same question, or what?
Yes.
Also, this providing demonstration for the large language model, isn't it the same as like one-shot learning? Basically, they just give one example to the model.
Yes, that's what I meant by demonstration.
But this is something proven in all papers that one-shot will improve zero-shot.
Yes.
They wanted to prove something which was proven already.
No, they wanted to prove that if you don't have demonstrations, zero shot, then those agents, multi-agents would improve. So it's like the explanations and answers from different agents coming from previous round could be something like demonstrations, could be more like alternative kind of. I don't really agree 100%, but could be like a new perspective of a demonstration. All right. Questions?
Yeah, you say the result of your research is that using multiple languages.
It's not my research.
That using multiple languages is improving the results.
Multiple large language models.
Yeah, large. And is there a comparison between the separate results from by themselves when you're just using one alone?
Yeah, the other one also showed Gemini versus
Yes.
Outperforming in all cases, only in both without repetition and description.
With this one single agent
Yeah, okay.
and then discussion. All right. No more questions.
Questions from remote meeting, maybe? Yeah,
Actually, I have a question.
Yes.
Is there a difference between the agents tokenized? So like maybe 6 agents like spend a lot of tokens. So like it's not really, it may not be like very.
What do you mean exactly? I didn't get the question.
Also like it also depends on it brings another question. So is it ChatGPT or GPT? 3.5.
ChatGPT.
ChatGPT. So because in actually prompting, so like when we ask questions, so like each word is a token. When it gives another answer, so it's all the answer is token. So like it spends a lot of money. So
Yes.
so like if there is 6 agents, it means that 6 agents will talk to each other. So like all of them gives another answer. So it's like multiplied 6 times tokens.
Okay.
So like
You are right. That's why, like in the first stage, we divide the agents into groups. If you have 6 agents, we divide them into 3 and 3, and then within the group, they will just see the explanations of themselves. So it's just like the answers from 3 agents would be provided in the prompt. So there's something considered because providing explanations of 6 large language models would be computationally expensive. Actually, to tackle this problem, there is a solution where we summarize the answer before giving it in the prompt of another
we can say
in another round. That was mentioned, yes, but not experimented.
Because at 6 times more expensive just for one fetch, it's just like, it was like 3% difference.
Yes.
So like, it's not a.
It's an important aspect to consider when researching. Okay, no more questions.
Thanks a lot again for the patience.
Thank you so much for attending.